In my earlier video, I had discussed about some question of linear algebra which had come different type of comparative exam. And today's goal of this lecture is I will see new type of operator, idempotent operator. This is our goal of this lecture. These type of operator are actually very important for not only comparative exam, higher study also. At first, see one easy type question which had come in CSIR June 2011 exam. Then I will discuss our actual goal of this lecture. The question is, let T be a linear transformation on the real vector space Rn over R such that the operator is here T square equal to lambda T for some lambda belongs to R. Then option 1, norm Tx equal to absolute value of lambda times norm x where for all x belongs to Rn. Option 2, if norm Tx equal to norm x for some x belongs to Rn, then lambda equal to plus minus 1. Option 3, T equal to lambda I where I is the identity transformation on Rn. And option 4, if norm Tx greater than norm x for a non-zero vector x in Rn, then the transformation T is necessarily singular. This is very easy type question. At first I will recommend you, please try to ownself. Then my method also. Okay. The operator is T square equal to lambda T. That imply obviously T minus lambda T equal to 0. And from this equation either T equal to 0 or T equal to lambda. If we consider T equal to lambda, then obviously, since at first notice the option, for this option, since here the question about norm, so if we consider T equal to lambda, then obviously norm T x equal to norm lambda x, which is equal to actually absolute value of lambda times norm x. Therefore, option 1 notice norm Tx equal to absolute value of lambda times norm x. And this is true for all x belongs to Rn. If we consider T equal to lambda, obviously this equation would be satisfied, and this is obviously true for all x belongs to Rn. Okay. If we consider the linear operator T equal to 0, then obviously this would be true. That means option 1 is a right option. And option 2 indicate if norm Tx equal to norm x for some x belongs to Rn, then that implies lambda equal to plus minus 1. For this option, since norm Tx equal to norm x, that implies absolute value of lambda times norm x equal to norm x. And from this expression, obviously that implies absolute value of lambda equal to 1. And absolute value of lambda equal to 1 means obviously that implies lambda equal to plus minus 1. Therefore, obviously option 2 also right option. If norm Tx equal to norm x for all x belongs to Rn, then obviously lambda equal to plus minus I. Okay. Let's see the option 4. Option 4 indicate if norm Tx greater than norm x for a non-zero vector x in Rn, then obviously T is necessarily singular. If norm Tx greater than norm x, that implies obviously absolute value lambda times norm x greater than norm x. And from this expression it implies absolute value of lambda greater than 1. And from this expression we can tell all values of lambda are non-zero. That means obviously our given T, operator T, is non-singular. That means option 4 is a wrong option, because option 4 indicate if norm Tx greater than norm x for a non-zero vector x in Rn, then T is necessarily singular. This is wrong option. Now let's see the option 3. Option 3 indicate if T equal to lambda I, where I is the identity transformation on Rn. Let's see option 3. Option 3 indicate if one linear operator satisfies this equation, then that implies T equal to lambda I, where I is the identity transformation on Rn. For this, consider one operator, this operator T equal to this matrix, and obviously T square equal to this matrix itself. That means T square equal to obviously 1 times T, and here lambda equal to 1. That means this has satisfied this relation. So we can take this matrix. But notice here this matrix satisfied our given relation, but T not equal to lambda I. That means option 3 also wrong option. If T square equal to lambda T, then that does not always imply T equal to lambda I, where I is the identity transformation for on Rn. That means only option 1 and option 2 is a right option. Are you getting? This is very easy type and very basic question. I hope my all viewers have understood this type of question easily, but very important. Okay? We will see our goal of this lecture. What is the idempotent operator? What is idempotent operator? We all of us know non-homogeneous equation Ax equal to B, when B is not solution of column space, then Ax tilde equal to Bc, where Bc is the actually component of B in the column space. Actually Bc is obtained by projecting B on the column space. Notice this is Ax equal to Bc. This is the projection of B on the column space, because this is the column space, and this B minus Ax bar is actually this is orthogonal to column space, and the projection operator on the vector B is, since these two vectors are orthogonal to each other, therefore just multiply this equation A transpose A x tilde equal to A transpose B. This is actually the normal equation. That means obviously x tilde equal to A transpose A inverse A transpose B. This is actually the best estimate. Then projection of the vector B on the column space BC is BC equal to A x tilde. Now put the value x tilde here. Then this would be A times A transpose A inverse times A transpose B, and this is equal to apply the inverse rules, A inverse times A transpose inverse A transpose B, and this is equal to actually B, and in this case B lies in the column space, hence its projection is the matrix itself, and when the projection operator. When a vector projected onto another space, then consider this picture. This is arbitrary vector B. Vector B is projected on the vector A, where P equal to x tilde A is the component of the vector B along the line A. Okay? And we all of us know a vector can be decomposed into two mutually orthogonal components. Therefore, B minus P is actually would be orthogonal to A. And since B minus P is orthogonal to A, that means obviously A transpose B minus P equal to 0, because they are in, since this is orthogonal, so their inner product must be equal to 0. And P equal to x tilde A. Now put the value. Then x tilde would be A transpose B over A transpose A. Are you getting? Where P equal to x tilde A. Now put the value x tilde here. Then this would be A transpose B over A transpose A times A. And since A transpose B be a scalar, so P equal to A transpose B over A transpose A times A. Okay? We can write this as A transpose over A transpose A times B, and this is not be scalar, this is be a matrix, and this is be a scalar. We all of us know. Since P equal to A transpose over A transpose A times B, so this P is actually the projection matrix which is multiplied by any B, which project it onto the vector A, and this is the picture. Notice B vector project on this line. Are you getting the picture? And this is the projection matrix. I hope my all viewers have understood what is the projection matrix. If A and B belongs to Rn, then obviously P is of order n cross n matrix. Then this matrix would be always symmetric, means P transpose always equal to P, and always this is P square equal to P matrix. That means if we square both sides, then P square would be actually P. Here I have considered the column space. So projection is the matrix itself, but otherwise the matrix would be singular matrix with rank 1. Actual definition of projection operator is: consider a linear transformation P from Fn to Fn be a linear transformation, then we say that P is projection if P composes P equal to P. And consider A be a standard matrix of P, then the property P compose P equal to P translate to A square equal to A. Then any matrix whose square is itself, that means we satisfy this equation, this is called actually idempotent matrix. That means another name of projection matrix is idempotent matrix. Here definition of idempotent matrix is always it would satisfy A square equal to A. Okay, and this is actually be the projection matrix. Are you getting what is the idempotent matrix, what is the projection matrix? Okay, comparative exam always will use idempotent matrix, not will use projection matrix. Always any question will be about idempotent matrix. This is actually projection matrix. Okay? Well, for example, consider this matrix. This is obviously the idempotent matrix because if we consider A equal to this matrix, then A square equal to obviously this would be this matrix. That imply here A is projection in R2 onto the x-axis where y coordinate is forgotten and any point of x-axis here of the form x comma 0. Are you getting? What is the idempotent matrix? Well, if we consider this matrix also, this matrix is also idempotent matrix and this matrix projection, notice the matrix onto the xy plane. Are you getting? Well, are you getting how look like the projection matrix? This is actually the standard form. Similarly, if we consider 0 0 0 0 0 0 0 1 0 0, that means this matrix also would be projection matrix who is project on the z-axis. Okay? And there exists other type of idempotent matrix. As for example, if we consider this matrix, then obviously A square equal to A. That means the matrix A is projected onto the line spanned by -1 1. Today I will stop here. In my next video, I will discuss the properties of idempotent matrix. But at first I will highly recommend you, please see today's video with pay attention because otherwise my next video don't be easy. But if you can to understand geometry of the idempotent matrix, then obviously properties also would be very easy. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.